anytime during this talk. So once again, my name is Parikshit. I work at VMware. I'm going to talk about multigroup fairness, indistinguishability, and loss minimization. This artwork is titled Relativity, so I thought it would be appropriate for the venue. So this is joint work with a number of wonderful co-authors, and I'll be mentioning their names as we go through the talk. So loss minimization, let's start by talking about what that is. This is the dominant paradigm currently for training machine learning models, and it's been extremely successful. Here's what it does. You have a class of models C that you're trying to train, let's say deep neural nets or random forests. You choose a loss function L, and then you try and find the class, the model C within this class that minimizes the expected loss under the distribution that you care about. Right? Now, this has been enormously successful. We see it all around us. Increasingly, its impact is being felt in spheres like social, medical, professional, political, legal. It's just everywhere, right? And with this increased reach comes greater responsibility, right? So one of the things that we've realized is that, especially in some settings like medical, legal, political, guaranteeing privacy and fairness from your predictions and your model is just as important as accuracy. And this is, in some sense, a weakness of the loss minimization paradigm, because if you're training your model to minimize your loss in expectation over a large population, which is heterogeneous, there is no particular reason to believe that it's going to necessarily look for good outcomes for, let's say, underrepresented populations, right? And I'm not going to talk about this in great detail, but by now there is a body of work in the research community showing that there are many situations in which it in fact does things that you do not want it to do, right? And this is not just in the research community. By now we've all seen articles like this, even in the popular media, that, you know, these machine learning models, they often tend to have biases, which we really would prefer they do not have. Right? So this brings us to the question of fairness and what constitutes fairness. Now, fairness is a topic that has been debated in, there's been scholarship on this for hundreds of years now. It is a very old topic. And of course, it depends on many complex things. It depends on what the context is. It depends on societal norms at the time, legal protections, and so on. Like, for instance, just to get some idea of how complex this issue is, let's think about the role that attributes like gender, age, and race play in hiring decisions versus in medical decisions. On one hand, in the first scenario, you have legal protections in place that protect you against improper use of these attributes, which is discriminatory. On the other hand, in medicine, it is very important that whoever is making these predictions appropriately adjusts for all these factors. And here, often you have the scenario where bad outcomes result for certain subpopulations because these factors are not being adequately accounted for, right? So even the question of what constitutes fair use is very dependent on the particular context. Also, we talk about models being biased. Bias, it's all pervasive. There's many different sources for it. At a high level, we can talk about biases in the data, which could be historical biases, biases coming from what attributes you decide to choose, or sampling bias. There could also be biases which are introduced by the model, by the model learning some kind of spurious correlations or focusing on things which are actually not what we think important or fair. Okay, so therefore, the issue of fairness is clearly a very complex issue, a very pressing one. And the movement, so this is an area which I'm relatively new to. Tony Pitasi, who's here, has been thinking about this for about a decade now. So there is a movement in the TCS community to say that, okay, one of the things that we need here is rigorous notions of what constitutes fairness, right? And the goal here is not to substitute for all this, rich body of scholarship that has been developed over these years, but to add to it, right, and to facilitate rigorous and open debate about the various notions, what their strengths and weaknesses are, and what the trade-offs between these various notions are, right? And one nice example of this, which I'm sure some of you are familiar with, was this discussion about the use of machine learning for making parole decisions. So there is a very nice paper about it by Kleinberg, Mulainathan, and Raghavan, and also an extremely, I thought, well-written and thoughtful article explaining what this paper is all about in the Washington Post. Right? So basically, the essence of this paper is to say that two notions of fairness, which on the surface, both of them seem extremely reasonable and desirable things to have, are actually incompatible with each other. So you're going to have to choose between them. Right? We'll come back and discuss this in a little bit of detail later. But one of the reasons why it's important to have rigorous definitions of what fairness is, borrowing from crypto and privacy, for instance, is that it often reveals trade-offs which you might not otherwise realize are inherent in in making choices about what fairness notion you want to go with. Today's talk is about other trade-offs. The trade-offs that we are going to talk about are between loss minimization and fairness, right? Are you giving up, intuitively people might think that when you try to enforce certain fairness guarantees on your model, then perhaps you're giving up something in terms of loss minimization or accuracy in order to achieve that, right? And we're going to dig deeper into these kind of trade-offs in today's talk. Okay, so here's an outline for the talk today. It's essentially in two parts, but the first part, we'll talk about the relation between loss minimization and multigroup fairness, when loss minimization actually leads to multigroup fairness and vice versa. Right? Then in the second half, we'll look at everything through the lens of indistinguishability. And we'll talk about fairness first. And by looking at it through the indistinguishability lens and drawing analogies to pseudo-randomness, we'll come up with this hierarchy of multigroup fairness notions that has certain desirable properties. And finally, we'll talk about loss minimization through the lens of indistinguishability. And here again, we'll see how the lens of derandomization allows us to come up with more efficient notions. Okay. So, so if there are no questions, you should stop me at any time if you have questions. Let's start by defining these various notions rigorously. So I'll just pause and see if there are any questions. All right. So let's start by talking about loss minimization and what we mean by loss minimization over a class of models C. So our setup is where there is a distribution D on points X and labels, which for this talk will all be binary labels, right? So you have a bunch of attributes. Each individual in this data set is being described by a bunch of attributes, and then you have a label. So this gives us a distribution on points X and labels 0, 1, right? Now, the moment you have a joint distribution like this, you can define what is known as the Bayes optimal predictor, where f star of x is just a point in the domain. It's the probability that this point receives the label 1 under this distribution, okay? So this is for us, in some sense, this is nature or the ground truth, right? And this is the thing that we are trying to estimate. A predictor is simply some other function which takes each point and assigns probabilities to it. And the goal here is to come up with an estimate for the Bayes optimal predictor in some sense. Okay. Okay. Now, of course, the Bayes optimal predictor is awesome. If we could learn that, that would be great, but it's often intractable for both computational and information theoretic reasons. And therefore, what you typically do in learning is you restrict the class of hypothesis to something which can be efficiently learned. I'm just going to introduce a bit of notation here. We'll have a base class C0 of predictors, which you should think of as something like decision trees, shallow neural nets, or deep neural nets, if you please. It is some class of hypotheses which is efficiently learnable, right? So these, of course, are predictors, which means they take values in 0, 1. But then I'll allow you a richer hypothesis class, which consists of arbitrary linear combinations of these base hypotheses. So think of going from decision trees to boosted decision trees. If I only take convex combinations, then at least I'm retaining the template of a predictor, since I still get values in 0, 1. Once I allow you arbitrary real valued combinations, then this is giving me some real values, and we're going to allow that as well. So C can also output its arbitrary linear combinations. It can return real values as well. Okay. Finally, the third ingredient, besides the distribution and the class of hypothesis, is a loss function. So here's the model. You get a point X, and then you take some action, T of X. You do this without seeing the label associated with the point. You decide, you're guessing whether it's going to rain today or not. You decide to take an umbrella or you don't. And then accordingly, you suffer a loss L, which is some function of the label Y, which is then revealed, and the action that you took. The first argument to L is, of course, the binary label. The second argument is a real value, right? It's an action. Typically, if you consider losses like squared loss, logistic loss, and so on, you have a loss function which is convex in this argument T, right? And we'll make this assumption in some parts of our talk. Okay, so now we have these three ingredients: a distribution, a class of hypotheses. Is there a question?
Yeah, I have a question. Why not allow the learner to see the label? That's normal to see the label.
Well, when you're making predictions, right? This is like, I'm defining what is a good predictor, right? So you decide.
You will predict it for things you haven't seen, right?
Sorry?
You normally will have a prediction for things you have not seen. You see some labeled examples, you
see some labeled examples.
And then you develop a hypothesis, which is supposed to do well on data points you haven't seen. But
on data points,
the learning process usually
the learning process will see the labels. It's the prediction process where you'll try to predict something without seeing the label. Like think of
okay, we learned already, and now you're okay. Got it.
Yes. So I mean, the loss function is what? Yeah. Okay. Yeah. Okay. So the goal of learning in the loss minimization approach is to find the hypothesis C, which minimizes your expected loss, right? You choose a particular hypothesis C, and then you minimize the expectation of L, Y, C of X. Now, how you do this, as Avi said, is that you have a bunch of training examples typically where you see both X's and Y's, and then you try and do some kind of optimization over it, right? Okay, but the whole thing which makes prediction hard is that even in the binary label setting, you take your action without knowing exactly which label it's going to be. If you knew which label you're going to be hit with, if you knew with certainty that it's going to rain or it's not going to rain, then prediction is easy, right? The whole point is the uncertainty about which label you will see, and therefore which loss function you'll be penalized by. Okay, so the way I've described loss minimization, it's not everything, right? But it does include a broad class of prediction, regression, and boosting algorithms. Things like AdaBoost, linear, logistic, LP regression, all of these are covered in the template that I described. Okay. Okay. So having described multigroup fairness, let's talk about, having defined loss minimization, let's talk about multigroup fairness. The first thing,
I have a question. What's an example that it doesn't cover? Like a important example?
Yeah, so I'm going to look at Guy for this. You could define loss functions which are allowed to depend on the point X, right? Like imagine that you wanted to define, you care about squared loss, but you want to restrict it to perhaps a certain subset of the population, right? So then you just write indicator of X lying in the subset of the population times the squared loss is my loss function, right? So I'm not allowing stuff like that.
Wouldn't that be included in the fact that the distribution would?
Well, yeah, so not really, because here I'm taking expectation on this base distribution on all the data, right? So I'm not allowing you to change the distribution here. Right? So, I mean, don't take this too seriously. There are many things we will say which really talk about these interesting sub-distributions and so on. That's one of the things where we are going. But just the way I have defined loss minimization, it doesn't allow you to do things like condition on subsets.
Parikshit, so does it cover things like checking calibration?
It does not cover checking calibration or even multi-accuracy, for instance, for the same reason. But yeah, so I'm just setting up, loss minimization in its most basic form. And, we will talk about interesting things like checking calibration as the talk goes on. So just, we'll get there. Okay, so now let me define multigroup fairness. What is multigroup fairness? Multigroup fairness, there's no one definition of it. There are many definitions which have been proposed in the community, and not all of them compatible with each other. At a high level, you have a large collection C of possibly overlapping subgroups or subpopulations. You want certain statistical constraints or guarantees to hold for each of these subpopulations, right? So this is the common theme which applies to all these definitions. Now, there are various notions like statistical parity, equalized odds, multicalibration. What is common to all of them is that they don't necessarily talk about losses, right? They are more concerned.
I have a question.
Yeah.
You picked C just to annoy us? The same.
Yes. Well, no. So you'll see that there is a certain duality in how C in loss minimization and C in multigroup fairness. For now, I want you to think of this C as populations. A couple of slides, and I'm sure it's annoying, but a couple of slides later, there'll be some payoff for this annoyance.
Okay.
Great question. Okay, good. So here I'm thinking of C as subgroups for which certain statistical constraints need to hold. And there are all these notions out there. And as we know, they're not even necessarily compatible with each other. The notion that we are going to focus on is multicalibration, which was introduced in this beautiful work of Hebert, Johnson, Kim, Reingold, and some other guy. So this multicalibration, we're going to talk about it in the binary classification setting. Although by this time, it applies to a lot of different settings. It can be applied in the setting of real valued labels, multiple labels, online learning, even in the semi-supervised setting where you're talking about importance weights. You have two distributions that you're trying to compare. The notion of multi-calibration makes sense. And in fact, this was work with Reingold, Sharon, and Bieder, which started me off on this multi-calibration path. And insights from here will be, I won't talk about this directly, but there are many insights from here which apply to the binary classification setting. Okay, so what are multi-accuracy and multi-calibration? So these notions were defined by Hebert, Johnson, Kim, Reingold, and Rothblum. Let me start by telling you what accuracy and calibration are. Let's think about a predictor who's trying to predict, a forecaster who's trying to forecast the probability of rain every day. So the forecaster says there's a 30% chance of rain, and then voila, it does not rain. So what does this mean? Was the forecaster right or wrong? This is the question that calibration tries to answer. The first notion is that of accuracy. The forecaster is accurate if in expectation their predictions are right. So let's say we look at weather forecasts for the entire year. On average, the forecaster predicts a 20% probability of rain, and then we find that it actually does rain 1 out of 5 days. Then we say that the forecaster is accurate. We don't look at the specific distribution of their predictions at all. So this is accuracy. David introduced this notion of calibration, which is a more nuanced notion. The problem with accuracy is that if a forecaster knows that in Princeton it rains on average 1/10 of the time, they need not even step outside. They just predict 1/10 every day, and then they are accurate, right? Because on average it does, it does rain 1/10 of the time. Calibration fixes this. It says that conditioned on a particular prediction of rain, like say 1/10, I want the expected label to be correct. So on days when the predictor predicts a 1/10 chance of rain, I want it to rain 10% of the time. On days when the predictor predicts a 90% chance of rain, I want it to rain like 90% of the time, right? So this sounds very good until you realize that it didn't really fix the problem that I was talking about earlier. The lazy forecaster could still look at this definition and then realize that their old strategy still works. I predict 1/10 every single day of the year. And then on the days when I predict 1/10, which is all the days, it does rain 1/10 of the time, right? So they're still good. But as you can see, this is heading in the direction of trying to make the forecaster work a little hard, right? So multi-calibration, think about, we're saying now that we're not just going to consider the whole year. I'm going to consider various sub-distributions. I'm going to consider January, February, March. Then I'm going to consider days of the year when it has rained 3 days in a row. I'm going to consider days when it's extremely sunny and it hasn't rained for the last week and things like that. And conditioned on each of these specific conditions, I want the calibration condition to hold. Now you can imagine that if it's been raining for the last 3 days, then the forecaster cannot just get away with saying 1/10, because probably on days like this, there is a very high chance that it's going to rain. So this is forcing the forecaster in some sense to come up with forecasts which more accurately capture the complexity of the Bayes optimal F star. And this is what multi-calibration is, right? So we say that F is C multi-calibrated, excuse the typo there, if it is calibrated, conditioned on every C in this class, right? So this is the original definition from this work of Hebert Johnson et al. And in this definition, you really need to think of each C in this class as being a Boolean function. It identifies a subset, or at least a positive valued function, so that it defines some kind of a measure so you can condition on it. What I'm going to work with today is a definition which was proposed in this work with Kalai, Reingold, Sharan, and Wieder, where we'll allow for real valued C's as well. So our definition says that for every C in the class and for every value 0, 1, the following condition holds. The expectation of Cx times this delta V fx is the indicator function that the prediction value equals V, times y minus fx is equal to 0. Right? So this looks like a mouthful at first. So let's try and unravel this definition. Let's think about the case when C is actually a Boolean function. In that case, doing this, I could just divide by the expectation of C on both sides. It's pretty much the same as conditioning on X lying in C. Similarly, this delta Vx, I could do a division trick and say I have conditioned on Fx equaling V. Now, conditioned on these two things, it's saying that I want the expectation of Y to equal the expectation of Fx, which is exactly what calibration asks you. You condition on being in C and the prediction taking a certain value, and you want these expectations to match.
So could you say again what delta V is?
Oh, it's the indicator function that Fx is equal to V. It's just a fancy way of writing, it's a fancy way of conditioning on the prediction taking on the value V. So the delta function is 1 whenever Fx takes on the value V, and it's 0 otherwise. So, okay. So you might rightfully ask, why did I take what was a very simple definition and write it in this way? Well, this has certain technical advantages. One thing, it allows C to take on real values. For another, really, we're not going to be able to ensure that this thing is ever 0 exactly. We'll say that this expectation needs to be small in absolute value. And this says that, it allows you to deal with events like C being extremely tiny. When C is very small, if all you get is random samples from your distribution, it's hard to give meaningful guarantees. This definition allows you to get a free pass for small set C, because just trivially, if you want a bound of alpha and C is smaller than alpha, then this condition holds, right? So this is just a uniform way of dealing with some annoying corner cases. What is multi-accuracy? Multi-accuracy is just the same condition, but without conditioning on fx equals v. So you just ask that for every C in this class, Cx is uncorrelated with y minus fx. So y minus fx are in some sense the errors that your forecaster makes, right? Y is the true label, fx is your prediction, so y minus fx is the errors in your forecast. Multi-accuracy is saying that there is nothing in C which is correlated with the errors in my forecast, okay? In some sense, the errors in the forecast look random to C. Multicalibration says that the same condition holds, but conditioned on f predicting a certain value. It's helpful to think of f as being discretized. Maybe it only predicts probabilities like 0.1, 0.2, and so on. So you condition on any of these predictions and you ask for essentially the same lack of correlation condition. So the nice thing about this definition, which I alluded to, is that C can be real valued. And just the way we've defined it, it gives us closure under sparse real valued, under sparse linear combinations for free. If actually you have error 0, then you can take arbitrary real values. If you have some error alpha, then you can take sparse real values. Another important difference, which will come up later. So we've said that you can take linear combinations of C. How about F? It turns out here that there's an important difference. Multi-accuracy is convex in F, meaning that if I take one predictor F that is multi-accurate and a second predictor F that's multi-accurate, arbitrary convex combinations of these things are also multi-accurate. It's just because expectation is linear. This property does not hold for calibration, right? And we could stare at this definition and try and see why this is the case, but actually we'll see a very simple example a few slides later. But this difference between the two notions, it's going to be important. It'll come up time and again in this talk. Okay, all right. So I'm going to pause here and see if there are any more questions, because this is very important to what comes next.
Yeah, maybe you could say a word about this definition of multi-accuracy, because it's not the same as minimizing a loss function.
Oh, yes, yes. Is it? We'll see. Okay, so this multi-accuracy, neither of these talks about loss functions explicitly, right? It's just asking for certain statistical guarantees from your predictor conditioned on a certain population. This is saying that conditioned on each population C, the expected prediction equals the expected label. And yes, there is no loss function there, right? So it is a pretty reasonable and rich notion, multi-accuracy in its own right. Neither of these talks about loss functions explicitly.
I mean, this could be very far from, just to say, this predictor could be very bad and still have low multi-accuracy.
So we have this, you're making a good point here. Neither of these notions are just, they are kind of analogy. It's like saying, what is pairwise independence? You fool a certain class of statistical tests. By almost any other measure, you could be very far from uniform, right? So that's exactly what multi-accuracy and multicalibration are. They are a class of statistical tests under which the ground truth predictor F star and your predictor F are indistinguishable, right? But it's not telling you necessarily that they are close in some other metric like L2 squared or something like that.
So Tony, I think it depends on the collection of sets, right?
Yeah,
Like if it's a really rich collection of sets,
Yeah.
then
Yeah,
it can be a meaningful guarantee.
Yeah, I agree, but it's always confusing to people because of the name multi-accuracy, and you don't just get it for free. And I know it's coming. You don't just get it for free, like it takes some and you have to address. Anyways, I just think it's worth pointing out.
Yes, definitely, right? Like these are, this is the whole, I guess this is the main difference here. These are, these are in some sense, we are saying these are necessary accuracy conditions we'd like a predictor to have. They are by no means the only things you want your predictor to have. right? Like these are just, certain rigorous guarantees we'd like from our predictors. And as Guy says, and this is going to come up in the talk again and again, what the collection of populations see you enforce this condition on is very important. If you enforce it on a very rich collection, then you get something really strong.
Yeah, I agree. It's just then computationally the task is.
Yes, and of course there's a price to pay for it as C gets richer and richer. But okay, so I think we are in the process of reconstructing the next half of the talk now. So let's get there in sequence. Okay, so Guy, this slide was after, yeah, so you'll see why the slide is here. So multicalibration is a very natural notion of accuracy. Why is it a notion of fairness, right? So I think here it's important to clarify that this is not an all-encompassing notion of fairness. Fairness has many aspects to it. Multicalibration is one of them. So why is that, right? Let's imagine that this machine learning model is being used, say, by a bank or a financial agency to hand out loans, right? What is the importance of this predictor being multicalibrated? Well, let's say the predictor is calibrated so that when for a certain population, we say there is a probability of 0.2 of default, it actually is the case for that for all these points, 20% of the time you do see defaults. Okay? So therefore, it's calibrated, but it's not multi-calibrated. What that means is that there is some subpopulation C in this group, such that if you consider the points which are given a score of 0.2 and which lie in C, then perhaps the risk is higher. Maybe actually the risk here is 0.3. So for the bank or financial agency, if all they care about is minimizing their risk, there is now an incentive to find out about whether a particular applicant is a member of C and treat them differently, because you know that the actual risk increases conditioned on being in C. On the other hand, if you are multi-calibrated, then safely you can say that if the prediction is 0.2, the bank or whoever it is ought not to care about any of these other attributes like membership within C or non-membership within C, because the expected risk that they face is the same regardless of whether you lie in C or not, right? So if you put out a model there which is not being multi-calibrated, then you are creating an incentive for treating people differently based on membership in these subgroups, right? So in general, the kind of guarantees that multi-calibration gives you is that your model is not allowed to make distinctions that are unsupported by the data, right? If it's trying to distinguish between two populations, you want this to be supported by what you're actually seeing in the data. What multi-calibration does not do is it does not protect against biases which are already present in the data. The ground truth predictor F star is always multi-calibrated. In some sense, what multi-calibration tries to do is to make your predictor F closer to F star, indistinguishable from F star for a broad class of statistical tests. But F star is always multi-calibrated. So if there are problems in F star in itself, which often there are because of historical biases and so on, multi-calibration does not protect against those. Okay. All right. So now we'll come to this question that Avi asked a couple of slides ago. What is the role of this class C, right? So C, we use the same C both in the loss minimization framework and in the fairness framework. And the role of C is that it imposes a collection of constraints on the prediction, right? It says that for these subpopulations, I want certain guarantees to hold. Now, on one hand, the right choice of C depends on the application. For example, in medicine, for instance, you can imagine that various kinds of conjunctions of attributes like people above a certain age with a certain medical history and exposure to some conditions, this might be a group that you particularly care about, right? On one hand, why not impose this for a richer and richer collection of sets C, right? the nice thing about multi-calibration is that you can always add constraints for free. You say that with regard to this population, I want it to look like the ground truth. With regard to this other population, and go on increasing the family C. From an accuracy perspective, this makes perfect sense. The limits come from computation. As C gets richer and richer, the task of auditing and coming up with a multi-calibrated or a multi-accurate predictor becomes harder from both a computational and a statistical viewpoint, right? So that's where the limitations of C come from. That's why you cannot say that I want C to be every subset of the universe. You just wouldn't be able to enforce such a constraint. Okay. So what is the basic minimum requirement computationally we need from the set C? One basic requirement, you could say, is that we should be able to audit for violations of multi-accuracy. What this means is that if there exists some C, which is correlated with the errors that my predictor is currently making, these errors are captured by y minus fx. If there is C which is correlated with these errors, then I ought to be able to tell this, right? This is a basic requirement. I need to be able to audit for multi-accuracy. This condition, it has been studied in the computational learning literature. It's known as weak agnostic learning, right? So what's going on here is y minus fx. Y is a label. It's either 0 or 1. Fx is a real value in the range 0 or 1. Their difference is some real value in the range -1, 1, which by randomization you can think of as a label, which is either -1 or +1, right? And weak agnostic learning is basically about saying that we should be able to distinguish our -1, 1 labels, which are correlated with some C, from random +/-1s, right? Which are not correlated with anything in C, by finding a hypothesis that exhibits some correlation. How do I tell apart the difference between the case when I am in this situation where there exists C such that the expectation of Cx times y minus fx is something, versus the case where I have Cx and then I have random +/-1 labels and there is no correlation? I should be able to distinguish these two by providing you with some other C which exhibits some correlation. It may not be the best C, but I should be able to find such a C. This is what weak agnostic learning is all about. In essence, if you stare at it, it's essentially saying that you should be able to audit this multi-accuracy condition. But once you're able to do that, it turns out by this beautiful result of Hebert, Johnson et al. That you can actually come up with a multi-calibrated predictor, right? And this ought to remind you of boosting. It is exactly the analog of boosting in loss minimization, right? Where it says that you can give me an inch and I can amplify it all the way to get something really strong. Okay. And so the limitation on C comes from the fact that we have to be able to perform this task called weak agnostic learning on C. Otherwise, statistically, the richer the class C, the better your predictor. Okay. So Tony, does this answer the question that you were asking a couple of slides back?
Yeah, it wasn't really a question. It's more that it's a lot more work to get accuracy with respect to a standard loss function this way. Just even for one group. So
oh, I see.
Multi-accuracy, I think, confuses people. So I just wanted to.
Okay, fair enough. Yes, there is some smarts involved in even computing something that's multi-accurate or multi-calibrated, right? Okay, so conditioned on this fact that we need C to be efficiently learnable, the class can be infinite. You could think about things like conjunctions, which are particularly meaningful in a medical setting. Shallow decision trees would generalize that. Deep neural nets, shallow neural nets would generalize even that, right? So this is what we're going to think of the class C as, right? And now hopefully it tells us why it's okay to think of C both as a set of weak learners, as in the learning setting, and as encoding a set of populations for which we want statistical guarantees, as in the multigroup fairness setting. Okay, so after this long preamble, we have loss minimization over C, and then we've defined multigroup fairness over C. Right? So I'm drawing these two pictures here. It's not really clear that I should be able to put these two things on the same canvas, right? For one thing, there is a type match. When you talk, the way I've defined loss minimization, you have real valued hypotheses, right? You come up with a real valued hypothesis, you suffer a loss. On the other hand, these group fairness notions like multi-accuracy and multi-calibration, they talk about predictors, which predict a probability of a certain label, right? The reason I've put this on the same canvas is that computationally, at least they lie in the same, they belong in the same space. Weak agnostic learning, it suffices for both these tasks. For loss minimization, this is a consequence of something like boosting. For multi-group fairness, it's a consequence of this HKRR algorithm. If you have a weak agnostic learner, you can minimize these losses. You can also come up with a predictor, which is multi-accurate or multi-calibrate. Right? So the rest of this part of this talk is going to be about examining the connections between these two notions. We're going to ask questions like, when does loss minimization yield multi-group fairness and vice versa? Okay, so let's jump into that. So let's start off with multi-accuracy. It turns out that it's actually quite easy to get multi-accuracy from loss minimization. This is joint work with Michael Kim, Mihir Singhal, who is an undergrad at MIT, who was my intern over this summer, and Shengjia Zhao from Stanford. What we show is that minimizing squared loss yields multi-accuracy. More precisely, minimizing squared loss over linear combinations in a class C gives you multi-accuracy with respect to the same class C. So why is this? Well, this proof, it's just intended to convince you that it's simple. I mean, it's not the proof that is important, but the length more, right? Multi-accuracy just requires this non-correlation condition to hold for every model CI in the class C. Right? And now let's consider predictors, which are linear combinations of the CIs. When you minimize the squared loss, your parameters are these coefficients lambda. What you're trying to do is to find the lambdas which minimize the expectation of y minus this summation lambda ICI squared. Right? So of course, this is a convex optimization problem. It's optimized at the point where the gradient vanishes. You compute out the gradient, you stare at it for a while, and you realize this is just saying that the predictor summation lambda ICI needs to be multi-accurate. Gradient vanishing is the same as multi-accuracy. Right? So this proof is, it's just a calculation. And what it tells us is achieving multi-accuracy for a class is in fact pretty simple. It is the same as minimizing squared loss for that class. And this is not isolated. If you were trying to do
Can I ask a question? So thinking about this and comparing it to what you already told us, that weak agnostic learning also implies multi-accuracy.
Yeah.
There's a distinction in that, I don't know, there maybe the loss wasn't the squared loss. And there's a distinction in that this is sort of, I don't know, I guess I think of it sort of as a cart production rather than, this is something Tony and I think talked about, rather than a Turing reduction. So how do you think about the distinction? I guess.
Well, firstly, this is not all that different from what I told you there, right? Because I said minimize squared loss. But how does this actually work, minimizing squared loss? You will call a weak agnostic learner at every step. You have a current linear combination. You compute out the residues, and then you ask, is there something in C which is correlated with these residues, right? And this is basically a weak agnostic learner, right? And then you subtract out an appropriate linear combination and you keep going. So weak agnostic learning is just this nice primitive which says, find me something correlated with these labels. Here, we are using this, wrapping a minimizer for the squared loss around it. Once the weak agnostic learner gives us something, we do an update which happens to minimize the squared loss at each step. What I was going to tell you in the next slide is that you could do a different update, an exponential update, which would minimize, say, the logistic loss, right? So these are all just, finally, these are all just variations on the same theme. You have a weak agnostic learner, you use it to make progress and get closer to F in some metric. Only the metric goes on changing.
But if you choose a different loss function. Yeah, I was wondering about, you answered my question before I asked it, but is it possible that different loss functions, I don't know, KL divergence or some other, you will get other notions of accuracy that are different and maybe valuable?
I feel like their gradient, okay, perhaps. Look, you can stare at what it means to optimize any convex loss function. It means that the gradient vanishes, and you can say that, okay, I want to understand what this condition means.
Yeah.
What I'm going to tell you is something slightly different, which is that for a very broad class of models, it means the same thing. That same thing is multi-accuracy.
Yeah, so my question is about, those who don't give multi-accuracy, but maybe give a notion that is, I mean, the very fact here is that what you're telling us is, given a loss function, it automatically generates a notion of accuracy, if you will. And maybe it's I don't know, useful notion. Maybe
I think, yes, come to think of it, I'm going to have something to say about it in an hour's time. If you, if you just ask me this question again, when I define this notion called weighted multi-calibration, we can talk about, I'll define the notion and we can talk about whether it's actually interesting.
Okay.
Right? Okay. So aside from squared loss and logistic loss.
Since we're long form, I'm going to. So I guess you, in a sense, you gave me an answer about kind of the algorithm. If that's my interpretation of it, you're saying that, there are all these different reductions and maybe they correspond to different algorithms that all can give you multi-accuracy.
Yeah. Maybe you'd like this, does this picture speak to you? So,
I don't know, does it speak to me? That's
So let me try and explain what this picture is saying. This is the space of all multi-accurate predictors. This is the space of loss minimization algorithms. In the intersection lies this family of algorithms or models called generalized linear models. These models, they try to minimize a Bregman divergence. Therefore, they always come up with probability distributions. They're optimal. The optimal for these things is always probability distributions. The optimal probability predictors, let's say, they always give you predictors. The optimal predictors for any GLM will happen to be multi-accurate. Each GLM will pick possibly a different multi-accurate solution in the space of all multi-accurate predictors, but they will all be multi-accurate. Right? So this perhaps is an answer to each of these algorithms is basically picking a different point in the space which optimizes a different loss function, but they're all multi-accurate, right?
I don't know if it matters, but I don't know what a generalized linear model is.
Sorry? Oh, no, just if you know what linear and logistic regression are, then we are on the same page. Generalized linear model is some grand generalization of this. You start with any convex function, you can come up with a generalized linear model. X squared gives you squared loss, x log x gives you logistic loss, but there is a generalized linear model for every, for every convex function. I just want to say that these are, when you have two things like this, you imagine that there is something more general hiding there. Indeed, there is. We don't need to care about what that something is. Okay.
Well, Parikshit, the picture does speak to me.
I'm glad.
I want to sort of highlight what I think is amazing about it. I think we kind of knew that algorithmically finding a multi-accurate predictor could sort of be reduced. I thought of it as a Turing reduction to different loss minimization problems. Maybe even a very simple one, which is weak agnostic learning. And the amazing thing about this picture is that it's not only that it can be reduced, and it's not even that it can be reduced using a CARP reduction, it's that it's sort of the same thing. You automatically, if you have a fixed class C and you learn a loss minimizer for it, I think you're saying that, you automatically get something that's multi-accurate.
Yes, for specific kinds of losses, the losses which come out of generalized linear models. Yes. So to pick up on what Guy said, The message here is that multi-accuracy is all around us in some sense. The most common models that people run are squared loss minimization and logistic regression, linear regression. These give you multi-accuracy. So there is no excuse for having models which are not multi-accurate. And yet it turns out that DNNs are not multi-accurate all the time, right? So what we've just said, it explains something that was observed empirically before by Gorabani, Kim, and Zhu, which is retraining the last layer in a DNN with, say, the logistic loss. It gives multi-accuracy with regard to the penultimate layer. So this is a bit of a circularity. You have a DNN, which is multi-accurate with regard to the features in the penultimate layer. Why is this interesting? Well, if you believe the penultimate layer is computing some kind of an interesting feature embedding, which encodes important demographic features, then you might want to be multi-accurate with regard to those features, right? And I should say that, again, this result was inspired by something analogous we proved in the semi-supervised setting, where we said that this maxent algorithm is actually giving you multi-accuracy. The takeaway, multi-accuracy is very easy to achieve. It's efficient, it's ubiquitous. How about multi-calibration? Wouldn't it be nice if I could write down some other loss function and say, hey, exponential loss, Ada boost, you run that, it's going to give you multi-calibration, right? That would be nice, but it's very unlikely. This is not a formal proof, this is intuition. The reason being that unlike multi-accuracy, multi-calibration is not a convex notion. So let me give you a simple example. Imagine that this is the ground truth. You have a population. For half the population, F star is 0. For the other half, F star is 1, right? Now the predictor, and C is the entire universe. I'm really talking about calibration here, not multi-calibration. It's calibration, which is not convex. So this is one calibrated predictor. The predictor which just says 0.5 all the time is also calibrated. But anything in between, any convex combination of these, like this predictor, which says 0.75 for half the population and 0.25 for the other half, is not calibrated. Because when it says 0.75, the expected label is 1. And when it says 0.25, the expected label is 0. Although almost by any measure, you and I would probably say that this is a better predictor than the 0.5 predictor. Maybe, but it is not calibrated, right? So this makes it very unlikely that I'll be able to just, at least to me, this makes it very unlikely that I'll somehow be able to write down some convex loss function and say that just by minimizing this convex loss, the outcome is going to be calibrated. Again, this is intuition, not a proof. And indeed, the known algorithms for calibration and multi-calibration, they are not gradient based. The HKRR algorithm, it has the flavor of constraint optimization. A classic algorithm by Mansour and McAllister from almost 20 years ago called boosting by branching programs. This is a cult classic in the computational learning community, although it never got as popular as Ada boost. This also gives multi-calibration. This is a more combinatorial algorithm. The takeaway is that these algorithms are not doing gradient descent as we understand it, right? And to achieve multi-accuracy, you could just do gradient descent, do squared loss minimization. Okay, so what this tells us is that this picture is somewhat misleading. We shouldn't think of multi-calibration as this, as this compact region of predictors. It's more like a set of islands swimming in a sea of multi-accuracy, right? Convex combinations of multi-calibrated solutions, of multi-calibrated predictors need not be multi-calibrated. Okay.
Can I ask something just to try to get some intuition? So if the predictor you learn respects like the sigma algebra generated by the C's, which is a very reasonable assumption, I guess. I mean, why wouldn't it? Then I guess multi-accuracy implies multi-calibration if the family of C's are closed under, I guess if it's an algebra, then it's obviously true, right? Because then any value is also like in the in the family C, right? But if it's
I
not,
think what you're trying to ask is whether multi-accuracy, multi-calibration can be seen as multi-accuracy for some richer family.
I'm trying to understand if there is a natural, I guess I'm trying to understand what's the natural sufficient condition on C such that multi-accuracy will also imply multi-calibration. So if they're like closed under
Yeah,
the unions, then this will be the case. But maybe something like
I'm not sure. Why do you think there is such a condition?
no, so I think if they are an algebra, like then it has to be the case.
So I think that you'll run into a problem.
This is a good question. I'd like to take it offline. I've thought about it, and I think at least in natural cases, it's not quite, it's
Let me give a short answer that may help Onen. So one thing that Parikshit has not talked about is that you really need these sets to have some mass in the distribution. Otherwise, the definition sort of doesn't make sense.
Wait. But for now, we said equal to 0. We didn't say like less than alpha.
No, but you really want to think of the situation where it's less than equal to alpha.
Okay,
right? That if you
so sure, then everything breaks. Of course. Okay, so it's crucial that we think about, because so far you
want to do things efficiently. Yes, you got to think about some error alpha there.
Yeah, and then then you definitely accumulate errors when you do intersections, and also I guess I shouldn't think about the family C as an algebra, right? It's definitely not closed under intersections. I'm just trying to get into,
think about neural nets of a certain depth, right? So maybe you can take pairwise intersections and so on. But then the complexity of the class goes on increasing. Right?
Yeah, sure. Okay, thanks.
Okay, great. Okay, so anyone asking a question, please introduce yourselves first, because I'd like to know who's asking me these questions. Okay, so now let's talk about, so we've said that loss minimization can give you multi-accuracy. It cannot quite give you multi-calibration. So is this the end of the story? Well, now let's talk about when loss minimization results from multigroup fairness. One problem, so this requires a bit of a digression. Right? One issue with the loss minimization paradigm is that it assumes that you know at the very outset which loss function you care about minimizing, right? And there are many scenarios in which the right loss function may not be known in advance, right? For example, if you're a public health officer, you're asked the following kinds of questions all the time. Should people with risk profile X be allowed to maybe attend a concert, board an airplane, work at an elder care facility, and so on and so forth, right? Now, these are problems which you can think of as binary classification with different false negative costs. The cost of allowing someone who is at risk of being positive to attend a concert is much less than the cost of letting them work at an elder care facility, right? So these are examples of tasks where the loss function you'd like to apply is slightly different for each one of them. If you knew the optimal predictor F star, then life would be simple. You'd just set different thresholds. You'd say that only people with risk probability less than 0.001 can work at an elder care facility. For an airplane, it's okay to be less than 1, and for a concert, I really don't care, right? But on the other hand, when you use the loss minimization approach, each of these comes with its own loss function, and each might in fact have a different optimal C, right? So really, to get rigorous guarantees, you need to retrain every time with a new loss function. Now, of course, there are things like transfer learning out there which say that maybe you're not really retraining from scratch. You can reuse something of what you've done. And there are a bunch of heuristics out there, but there is nothing by way of rigorous guarantees which says that here's a way to get something which is simultaneously optimal for this loss function and for that loss function, and for some other loss function you didn't even see before, which you're suddenly now having to optimize for. Right? So this is something that's clearly, and I've drawn this picture here, which I'm not going to explain, but this picture is meant to show that even in very simple low-dimensional scenarios, for very simple classifiers, two-dimensional classifiers, if you change the cost of if you change the false negative cost, you in fact have a different optimal hypothesis C. So this is something which is clearly calling for a good definition. And in this work with Kalai, Reingold, Sharan, and Wieder, we put forth a definition, which we call an omni-predictor, which is one predictor to rule them all. So the setup here is that you have a family L of loss functions and a hypothesis class C. An LC omni-predictor is a predictor F, such that for every loss in the family, there exists a simple univariate post-processing function P, okay, such that you can do the following. If you care about minimizing the loss L, what you do is that you just post-process the predictions of this predictor, and the guarantee is that the loss that you'll suffer is less than the loss of any hypothesis in the class C, including the single best hypothesis in C, which is chosen to minimize this particular loss. Okay, this is what an omni-predictor is. So let me say that again. You look at your data once and for all. You don't know what loss you're going to optimize later. It's going to be some loss from this family N. You come up with a predictor, and then you throw the data away. You are done learning. Now someone comes up to you and says, I care about this loss function M. Then what you do is this very simple post-processing of the predictions, which pretend like this predictor, let's just pretend that this predictor we have is actually the base optimal predictor. If someone says that I want to minimize the L2 squared loss, then I will do nothing. The post-processing is identity. I just output the predictions themselves. If someone says that the loss function I care about is the L1 loss, then you do this rounding, where if the probability is greater than 0.5, you say 1. If it's less than 0.5, you say 0, right? So you do just, when you learn what the loss, when you find out what the loss function is, you just do the post-processing that's appropriate for that loss function. But the claim is that in doing so, you are doing better than the best hypothesis in C, which is being chosen with knowledge of the loss function by, say, minimizing, by running L2 squared regression if it's the squared loss, by running L1 regression if it's the L1 loss, by running logistic regression if it's the logistic loss. So you have this one predictor which is competing with the best hypothesis found by a custom algorithm for each loss function. Right? So you train once and for all for the entire, you don't care about the specific loss function L. You just train based on the data. The only way the loss function influences what you do is in this post-processing. So this sounds like a really broad thing, right? I'm telling you that at one fell swoop, I want to compete with logistic regression, linear regression, AdaBoost, a whole bunch of different, bespoke algorithms. Is this even possible? The reason it's possible is that the base optimal predictor is an omni-predictor for all L and C. Okay. So this is kind of folklore, but let me just tell you intuitively. I'm sure this is fairly obvious to you, but let me just tell you intuitively why this is the case, right? So if you knew what the label was going to be, then choosing the best action is a triviality. If somebody tells you that, this person, is positive, then you know what to do. You say, don't go there, don't do this, don't do that, right? The whole point is the uncertainty. You don't know whether the label is 0 or 1. Now, if someone tells you that, look, the label is being generated probabilistically. With probability 10%, it's going to be 0. With probability 90%, it's going to be 1. That is just as good as far as minimizing your expected loss goes, right? Because then you say, oh, with probability 10%, I'll suffer this loss. With probability 90%, I'll suffer that loss. Now I have a simple convex minimization problem to solve, and I will solve it. So that is exactly what this post-processing function P star is doing, right? And there's nothing you can do which is better than this. So F star is telling you for each point what the probability of labels is. Once you have this information, it's very easy to make optimal choices. Now, the fly in the ointment here is that this T star function, this post-processing function, is of course easy to compute. The trouble is that computing the base optimal predictor is hard. So omni-predictors, of course, they do exist. The question is whether they can be efficiently computed, and for an interesting class of loss functions. So this brings us to our main theorem, which draws the connection to multigroup fairness. We showed that if F is multi-calibrated for C, then it is an L, C omni-predictor, where L is the class of all convex Lipschitz loss functions, right? Moreover, the post-processing that you do, there's no cheating going on in the post-processing. It's the same post-processing you do if you had the base optimal, nearly the same processing as if you had the base optimal function, right? The fact that L is convex is important. The Lipschitzness condition, you can relax that a little and say it only needs to be Lipschitz in some region. But this theorem, it includes all the LP losses, logistic loss, exponential loss, hinge loss. Every loss function which I'm aware of is included, and people really care about, is included in this class of loss functions. Okay. Okay. So let's go back to this picture now. We said that there is a loss minimization approach to get multi-accuracy. There is no such thing for multi-calibration. In fact, what we're saying is that there is a connection in the reverse direction. Once you have a single multi-calibrated predictor, you can minimize any convex loss function you like. If you want to compute with Ada boost, minimize exponential loss, there is a post-processing you can do, which guarantees that you're at least as good as Ada boost. If you want to compete with linear regression, there's no post-processing, just the predictions are good enough. Similarly, if you want to compete with some other loss function that you never heard of before, but it happens to be convex in Lipschitz, there is a simple post-processing that lets you do that. Right? Okay. So why is this interesting? Well, firstly, it's interesting because it has this good karma feel to it. The authors of the original multi-calibration paper have sworn to me that they weren't thinking of loss minimization when they defined this notion. They were solely motivated by multi-group fairness. And it's very interesting that this happens to give you an extremely strong loss minimization guarantee, so strong that we had to come up with a new definition to capture it, right? And then it tells us something new and interesting about multi-calibration itself. So what we propose in this work is a new way of thinking about multi-calibration, not as a predictor, but as a partition of inputs which enjoys certain pseudo-randomness properties. So here's our view of multi-calibration. Multi-calibration with regard to a class C means that you partition your input space into regions, where within each region of the partition, the following pseudo-randomness condition holds. The expectation of Cx times y is the expectation of Cx times the expectation of y for every hypothesis C in this class. Now, of course, if Cx is Boolean, then this is basically saying that Cx and y are independent condition on this partition. Now, if Cx is real valued, it's not Boolean, then this is just a first order condition. It's not true independence, right? So of course, I've just given you this condition on this partition. I haven't told you how to come up with a predictor based on it, but the predictor is the obvious one. Within each state of the partition, just predict the expected value of the label. So in this picture here, I predict 0.2 in the blue region, 0.4 in the red region, 0.6 in the green region, and 0.9 in the other region, right? So this predictor is a multi-calibrated predictor. So why is this the case? Let's just, match up this definition to the definition that I presented previously. Fixing a partition because of my way of defining f is the same thing as conditioning on the value of fx. If two partitions happen to have the same value of fx, no worries, we can merge them together, right? Now, conditioned on this value of fx, what I would like is the multi-accuracy condition, which is that the expectation of Cx times y minus fx should be 0. But fx, I have defined to just be the expectation of y. So this multi-accuracy condition here is exactly saying that expectation Cx times y is expectation Cx times expectation of y. So indeed, this is just the same definition in a different guise, right? Okay, so the intuition here is that we've partitioned the input space into regions such that the labels within each partition of this region, they look random to see. It's essentially a pseudo-randomness kind of partition. And this idea, there's a very elegant formalization of it, which was very surprising to me in this outcome indistinguishability framework of Dwork, Kim, Reingold, Rothblum, and Yona. And we'll talk about this some more a little later. Okay, so this suggests multicalibration as a solution concept for learning, right? So multicalibration I think of as a loss-free view of learning. So the philosophy of loss minimization for learning is like cramming for a test, right? You know that you're going to be asked to minimize this loss function. You do everything you can to minimize that. And if for some reason a different loss function shows up in the exam, then you're screwed, right? On the other hand, what does multicalibration say should be the goal of learning? Learning is taking something you're observing and decomposing it into a structured hypothesis and pseudo-random noise. The structured hypothesis here is this partition into regions. And the intuition is within each region, it's as though every point is deciding its label by tossing a coin. So the points in this region, they toss a coin which has a probability 0.2 of being heads. In other regions, the bias of the coin changes, right? And this model we have, it's indistinguishable from the reality to any hypothesis from the class C, right? So it suggests this very nice structure versus randomness decomposition. Like this stuff, I happened to be at the IAS back in 2007, and that's when, the structure versus randomness decomposition was new, and there were a bunch of exciting results around this. So, well, we've come full circle now. Multicalibration is suggesting this kind of a structure plus randomness view of learning, right? And then there's a ton of connections to agnostic boosting, right? Which is again, yes.
Just a second. The proof of this, I assume, is the same multiplicative weights.
No.
The finding of the partition, I mean, or not?
This is okay. So this is basically the Mansour-McAllister boosting by branching programs algorithm. I can just tell you very quickly how it goes. It's, I think, some baby version of the Zemeridi decomposition. You can think of it as. Everything is initially in a single partition.
Yeah.
Then you see whether there is, and your predictor is the expectation, right? You see if you can find a C which is correlated with this, right? You find which is correlated with the errors.
Oh.
If you can, you use that C to break this region into two parts. Okay? Mm-hmm. And then you recurse. When you have regions such that the prediction on those is the same, you merge them. Otherwise, you check the pseudo-randomness condition within each partition, and if it doesn't hold, you break. You go on doing this, you're making progress, so eventually you'll converge. This is basically Mansour-McAllister, beautiful algorithm.
So why what are the branching programs there? I mean, that seems to be, the usual refinement argument with the...
Oh, well, the representation is a branching program. How do you represent the partition?
Does it have to be? I mean, is a...
I don't know of a simpler way than that for coming up with, look, this partition view and the original view, it's all the same up to some discretization. I could take Guy's algorithm, take the outputs and kind of, stare at it for a while and say, okay, here's my partition. So in some sense, they're not fundamentally different, I would say.
Okay.
These are equivalent notions, more or less. The important thing in a multicalibrated predictor is not so much the values it's giving, but the set of points that it's giving those values to, right? Once you decide what set of points is in your cohort, your value is kind of dictated by multicalibration. It needs to be the expectation for all of you.
Right.
All right. Okay, so another nice thing is that this highlights a lot of connections to this notion of agnostic boosting. Starting with our definition of what is multicalibration itself, it's inspired by definitions in the agnostic boosting literature. The algorithm which I just described is this boosting by branching programs due to Mansour McAllister building on Kearns and Mansour. This algorithm, we've always known it's stronger than things like AdaBoost. Now we have a new language for that. We can say that this gives us multi-calibration, whereas those other boosting algorithms only give you multi-accuracy, right? And we've known that these branching programs, they have some superior noise tolerance properties. And by taking our omni-prediction result and just specifically applying it to the L1 loss function, we can get better guarantees. The L1 loss is known to be closely connected to agnostic learning, and we're able to prove a stronger result about boosting by branching programs and use that to give alternate proofs and unified proofs of a bunch of results in computational learning. Actually, this last bullet is a bit misleading because it's double counting here. The goal of these last two papers was to give alternate proofs of the first two papers. They did it by giving a custom boosting, agnostic boosting algorithm. What we're saying is, well, actually, this Mansour McAllister algorithm from 20 years ago already gives you this kind of strong agnostic boosting guarantees, and it reproves all these results. Anyway, okay. So now let me sketch the proof of this omni-prediction result. Why is it that multi-calibration implies omni-prediction? So this is just going to be an intuitive proof, not a fully rigorous one, but I hope it conveys the main ideas. So what is multi-calibration? It gives us this partition of the input space into regions S1 through Sm, where conditioned on each Si, we have this pseudo-randomness condition that Cx times Y is equal to expectation Cx, expectation Y. And then the predictor, it just predicts the expected value within each region, right? And now we have to show that by post-processing these things, we get something better than anything in C. So let's start. The first lemma is this, right? Fix a particular loss function. If we restrict ourselves to only outputting the same action for every point in the state, it's a strong restriction. But if we restrict to this, then the best action is to just take our predictor and post-process it. Okay? So I claim that if for some reason you were only interested in outputting one action for every state, then the thing which we are doing is the best thing to do. Now this proof, it just is pretty much from the definition of what this Bayes optimal decision T star is. And I've kind of sketched this before, but I'll say it again, right? So T star is the following function. If the probability of 1 is P and 0 is 1 minus P, it tells you what action to play to minimize your expected loss. How does it do that? It finds the T which minimizes your expected loss, which is P times L1T plus 1 minus P times L0T. This is what T star is. Now, if I tell you that for this entire state Si, where the probability is 0.4, you have to play the same action. What would you do? You would play T star of 0.4, because with probability 0.4, you'll suffer the 1 loss, and with probability 0.6, you're going to suffer the 0 loss, right? So the best action is to just take the probability for this state, which happens to be our prediction, and apply T star to that. Okay. So this is an annoying technical lemma. There's really no syntactic content to it. It's just about this is how T star is defined. Okay. Now, C, of course, it doesn't take on a single value per state. It can do anything. It can take on a different value for every single point in the state. But because the losses are convex, what we can say is that C is better off playing 2 actions per state than playing a whole bunch of actions per state, right? Like taking on a whole bunch of different values. Rather than taking a whole bunch of different values within the state, the loss would be minimized by just taking 2 different values in a state. So why is that? Let's define the function C2 as follows. So we have a joint distribution over X and Y within a state. So let's first imagine sampling Y and then condition on the label sampling X, right? And then just think of the function C2, whose value is the conditional expectation of C given the label. So whenever y is 0, C2 takes on the value, which is the expectation of C conditioned on y is equal to 0. Whenever y is 1, it takes on the value expectation of C conditioned y equals 1. Now, I'm expecting someone to say that, hey, this is not really a function because you need to know y, right? And of course, a function is just allowed to look at x. So just for now, assume that the ground truth f star is Boolean, right? Like there are some points which the label is always deterministically 1. There are other points where the label is always deterministically 0. And therefore, C2 is just partitioning every state. For the 1 points, it's outputting a single value, which is the expected value of C conditioned on those points. For the 0 points within the state, it gives the expected value of C conditioned on those points. Okay? So now this two-valued function C2, its loss minimization, the loss it suffers is even less than the loss of C. It's better than C. This is a simple consequence of convexity. Once you fix the label, you're suffering a convex loss. So rather than going all over the place and suffering a large loss, you just play the expectation, then your loss is less. Okay? So rather than C playing all these values, it would be better for C to just play these two values. Okay? Of course, note that we haven't used multicalibration yet. So that needs to come somewhere. That comes in the last lemma, which says, well, now rather than two values, because of multicalibration, you might as well play one value. That one value is the expected value of C for this entire state. The reason is the pseudorandom condition. Expectation Cx times y is expectation Cx times expectation of y. So if you do the usual messing around with expectations, which I'm not going to do here, you'll see that conditioning on y doesn't change the value of Cx by much, the expected value of Cx by much. If it did, you wouldn't have this condition, right? So if you just define the value, C is the if you just define the expected value of C for the entire state, you'll see that it's exactly, these two values, if you assume multi-calibration with no error, that exact equality holds here, then these two conditional expectations are not different. They are the same. If you have some multi-calibration error, then they are not exactly the same. They are close by. And that's why we need the Lipschitzness here. But we can just replace these two values within each state by a single value. And now we are done. We have that we are playing the best single value, C1. We are playing the best single value. So it's better than playing the expectation of C for the entire state, which is almost as good as playing the conditional expectations, which is better than playing C, right? So, okay, so this is just meant to be an intuitive proof sketch. I mean, really, I think there's nothing technically deep going on here. It's really a question of having the right definitions in place. So let me pause here and see if there are any questions. Okay. So we are quite far. We are almost 1.5 hours into the talk, but I think that this is a good time for a break, right? So let me just say one more thing, and maybe, I don't know, Tony, is it conventional to take a break in this seminar?
Yeah.
Oh, sorry about that. I should have broken a long time ago, but okay, let me just say one more thing. This theorem, it uses convexity in a very crucial way. Multicalibration does not imply omni-prediction for non-convex loss functions L. You can come up with a very simple example, basically based on 3 bits using the parity function, but I'm going to skip this in the interest of time, right? So the takeaway from this part is that multicalibration and loss minimization are not in conflict, far from it. In fact, multicalibration gives you a very strong form of loss minimization, which we call omni-prediction. Okay, I suggest we break now, and when we come back, we'll get indistinguishability into the picture.
Parikshit, let me add to, because no one wants the break, so they want to hear me speak instead, I'm sure, that I do think for general loss functions, there is a connection to multicalibration. It's just,
Oh, sorry.
Sets would need to change.
I'm sorry. Yes, I should say C multicalibration C multicalibration does not imply L, C omniprediction for arbitrary N. A guy and gal have this nice result where you make the class. The interesting thing about this theorem, the theorem which has now disappeared, is that you just needed multicalibration for the class C, and you got all convex loss functions. If you want to make the class of loss functions more powerful, you would need to beef C up as well. And I think this is done in this very nice work of Guy and Gal. Is this accurate, Guy?
Yes, I think Gal also gave a talk about it a few weeks ago, so everyone remembers.
Fantastic. Okay, sounds good. So what I really wanted to say here is that if you just have multi-calibration for C, you cannot get omniprediction for non-convex loss functions when you're comparing with C. Okay? And now I'll actually stop and let everyone take a break. Tony, is 5 minutes the conventional length of break?
I think that's fine.
Okay, sounds good.
I left phone call and then I went to the bathroom and it was locked, so I waited a few seconds. Apparently it was locked because Einstein was in the bathroom. And I have no idea who he is. Like, even seeing him from close, it doesn't look like anybody familiar.
Yeah, so I'm saying to me,
I mean,
it doesn't look.
besides
Sure.
Einstein.
You know that guy, I forget his name, Garrett or something or other? Could it be him?
No, like I thought it should be him by the cast, but it doesn't look like him at all.
I see. Yeah, this is too hard to see from here. All these screens.
Well, we can go to the watching deck.
Yeah, okay.
Apparently they are coming in a lot today because they got tired of the portable bathrooms. But this is happening outside.
They did have carpet feeding.
At least it's for this one of the directors.
Do you know what movie?
Yes. Okay.
Where is it filming even now? Is it way over there? Where?
You see the something looks like a level on the ground.
Yes.
So the camera is the big point towards the front.
Okay. Nobody's acting right now.
Because I've done something.
Maybe it's for 10. אפשר לבדוק את זה אצל רופא. זה מעשה לבן.
ויש שניים, אז בטח אופנהיימר.
יש לו כובע. Same scene for like 4 hours now.
Yeah. You want it to be an answer.
They have the scene so many times that they don't need to record it.
They have a beautiful.
In the morning it was raining, so maybe they are redoing what they did before. So I can tell you the entire scene, but I think that one of them has his edge falling down and open up his the head. This is like 10 seconds that they film or something like 100 times.
You need to watch this movie. I hope it's good.
So I hope that the edge falling scene would be amazing.
Hopefully it is a movie.
Maybe if you look at the card on the frame, we can do it see ourselves.
Yes, the cameras are very, very good.
אפשר לשאוף משהו גם שיש משהו שפספסתי בזמן שחלמתי.
אוקיי.
זה ברור שאם אתה עושה שם קוודרטיק לוס, אתה מקבל multiaccuracy. כמעט מההגדרה.
הוא הראה את זה גם.
כן. עכשיו, בדרך כלל, עקרון יחיד שנותן multiaccuracy. זה הגנרי, כאילו...
כלומר, אתה שואל או אומר?
אני שואל, אומר.
אני לא חושב שיש פתרון יחיד.
כאילו... לא תמיד. לפעמים יש שם לנדסקייפ כזה, אבל זה כאילו מרגיש לי מוזר, כאילו זה מרגיש לי שבמקרה הגנרי, minimization, logistical כי אתם פתרונות שונים, למרות שיש רק פתרון אחד שנותן multiaccuracy.
אז אני לא חושב על זה ככה, אני חושב שיש לנדסקייפ של פתרונות, בפרט יש את הבייס אופטימל פרדיקטור, שהוא פתרון טבעי, פתרונות שהם לא הבייס אופטימל. אז כאילו, בוא נשים לב שהפתרון הוא לא...
Yeah, I think it's good to start.
Okay.
Yeah, thanks.
Yeah, welcome back, everyone. So let me start by saying that I know this slide looks a bit scary. It suggests that I'm only 1/3 through my talk after 1.5 hours. That's actually not the case. I am halfway through my talk, and I don't intend to go double the time. But we get to the really fun part now, which I haven't talked about before. So I have no idea what's coming next. So we're going to talk about the notion of indistinguishability now. And this is something which, okay, let me just set it up first. We've seen multicalibration is this really awesome and powerful notion, right? But it comes at a cost. The cost is rather high sample complexity. And this comes about because ensuring multicalibration requires conditioning on various small probability events. It seems like, perhaps this is inevitable because multicalibration is giving you this extremely strong guarantee, right, about loss minimization. So it requires a very fine-grained understanding of the distribution. Be that as it may, this is a bottleneck for real data sets. You really need a lot of samples. In the multi-class setting where you have D labels, everything, forget the multi, just calibration everything becomes exponential in D because your probability predictions are now vectors of probabilities in D dimensions. So conditioning on a certain prediction and so on becomes very expensive, right? On the other hand, multi-accuracy is just great, no matter what the number of dimensions. It's just linear regression. It doesn't get any simpler than this, right? So on one hand, you have this notion which is relatively weak, but extremely easy to achieve. On the other hand, you have this extremely powerful notion which comes at a great cost. Naturally, we'd like to ask, is there some nice and natural way to interpolate between them and have the best of both worlds? This is what we're going to do in the second half of the talk. And the road through them, it passes through pseudo-randomness. Right. So this connection was made in this beautiful work of Dwark, Kim, Reingold, Rothblum, and Yona, where they asked this very basic question. What does it mean that a predictor F is correct? Right? And they take a pseudo-randomness approach to it. They say, let's think of a family of distinguishers which have the following inputs. They have the point X, the prediction Fx for that point, and the label Y, right? And now the predictor is trying to distinguish between two scenarios. So what are those two scenarios? In one scenario, your label Y is being generated according to nature, right? So you can imagine that in that case, Y star, the label, is being generated according to the base optimal predictor F star of X. In the simulation of nature, though, Y is actually being generated according to the predictions of F of X. What that means is if for this point Fx is 0.7, then we flip a coin, which is heads with probability 0.7, and then we say 1, or it's tails with probability 0.3, and then Y is 0, right? So these are the inputs to your distinguisher, and the distinguisher is supposed to accept or reject based on its inputs, and distinguish between the case when the samples are generated according to nature and the simulation of nature, right? And checking for C multicalibration is one example of such a distinguishing family that we've already seen. Because when I simulate labels according to Fx, it's trivial that, Fx is going to be multicalibrated for this distribution because, when it says a certain probability of something happening, that is exactly the probability with which it happens. On the other hand, Fx may or may not be multicalibrated with respect to nature. And fooling multicalibration can be viewed as exactly fooling this particular family of tests. So what the main result of this, I think the main contribution of this paper is this very beautiful definition, but their main result here, one of their main results is that for Boolean distinguishers, which either accept or reject, this notion of fooling these tests is called outcome indistinguishability. Outcome indistinguishability is basically multicalibration for a family of tests which can be derived from the distinguisher A. I'm not going to get into the precise notion of how you get this family CA from the distinguishers A and so on. That's not important for us. So multi-accuracy is distinguishers which get access to X and Y, but not to the predictions F of X themselves. Right? So this is what this outcome indistinguishability paper shows. Now, what we are going to do is certain variations, as I think of them, on the theme of outcome indistinguishability. So this is done in two works. One is this work with Kim, Singal, and Zhao that I already mentioned earlier. The other is ongoing work with Kim, Reingold, and Wieder. Right? So one of the things that we do is to consider real valued distinguishers. So now you can imagine a distinguisher which instead of outputting either 0 or 1, it outputs a real value. Some bounded real value, let's say, not even necessarily in the range 0, 1. And then we compare the expected value when the samples come from nature versus when they come from the simulation. Now, the main thing that we will do is focus on restricted tests that encode various kinds of fairness and optimization desiderata. For example, we might measure, say, the correlation between Y and the predictions F of X. We might consider some particular loss function like the LP losses, or if you're interested in omniprediction, then you could compare the loss when you play according to some hypothesis from C versus when you use the predictions F, and see if the difference between these two, the gap between the losses, it changes under Y versus Y star, right? So I got to say again that before Guy corrects me, that something similar has been done before in the work of Rothblum and Yona. What we are going to do differently is to work with very restricted families of distinguishers which are particularly of interest in the fairness and optimization scenario. The intuition here is that to fool a restricted class of tests, you may not require the full power of multicalibration. In this view of the world, multicalibration is like this very powerful pseudorandom generator, like say Yao or Nissan Wigderson or something. Given a family of tests, multicalibration says that, well, if you can be multicalibrated for this family of distinguishers, then you can achieve outcome indistinguishability for this family of tests. We are interested in very simple families of tests. And what we're asking is something like, what is the analog of things like bounded independence in this setting, right? So I know that it sounds a little bit vague right now, but we will make this concrete shortly. Okay, let's start by searching for the right analog of bounded independence, right? So this is joint work with Kim Singhal, and Zhao. So let's start with multi-accuracy. This is just the definition of multi-accuracy, that expectation of Cx times y minus fx is 0. We can view this as matching first moments of f and f star conditioned on C. Because I can just rewrite this to say that expectation of Cx times fx is expectation of Cx times f star x, right? So multi-accuracy is matching first moments. Multi-calibration is full indistinguishability in some sense. Is there a notion of matching the second moment and matching higher moments? Here is one candidate definition. We say that for all C in C, I want the expectation of Cx times fx squared is expectation Cx times f star of x squared, right? It seems like a perfectly reasonable constraint to ask from your predictor f. What is unclear is how you're going to enforce this. Because remember, we don't get values for f star. We just get binary labels whose expectation is f star. So you have no way of looking at a point x and saying f star x squared is something. You just saw a label for it, which was either 0 or 1, right? So it's not clear that this is the right notion of moment matching because we get access only to the labels. And just for those of you who have seen this work by Jung et al. On multicalibration for real values, they were interested in a setting where the labels themselves were real value. Okay, so it made sense to think about higher moments. Our labels are binary. So just, if you're not heard of this, great, but otherwise, please don't be confused by what they're doing there. How about this as a notion of moment matching? We ask that expectation Cx times fx squared is expectation Cx times fx times f star of x. Now, at first, this looks a little weird, right? But it has a couple of things going for it. For one, if f were equal to f star, if you actually had the base optimal predictor, then this constraint would be satisfied. So in some sense, it is a valid constraint. Secondly, you can actually enforce this constraint just from random samples because it is linear in f star x. This constraint I've written here is equivalent to saying Cx times fx times y minus fx should equal 0, right? Okay, so it's a valid constraint. You could possibly enforce it, but why is it natural? Why does this make sense? And why is this some kind of an analog of bounded independence? So let me define what we call low degree multicalibration. Just to remind you, this is multi-accuracy. Cx times y minus fx is 0. This is multicalibration, where Cx times delta of fx times y minus fx is 0. Here is low degree multicalibration. For all polynomials p of degree k minus 1, I want that Cx times p applied to fx times y minus fx is 0, right? So I'm allowed to come up with some weight function which depends on the predictions. Now, if k is 1, then I'm allowing polynomials of degree 0, which is constant functions. So what I get here is simply multi-accuracy. If I allow myself polynomials of arbitrary high degree, then I can do all kinds of polynomial interpolation tricks. I can use something like Lagrange interpolation and write this delta function as a polynomial of sufficiently high degree, right? So as the degree increases, I'm approaching multi-calibration here. In between, I have this intermediate notion, which I call low degree calibration. And again, I'm cheating a little bit here because instead of 0, you need alpha. And then you need to restrict the L1 norm of the polynomials or something like that. But let's ignore that for the time being. So what this gives us is a hierarchy of fairness notions that interpolates from multi-accuracy, which is the first level, MC1, to multi-calibration, which is what you get when you allow polynomials of arbitrarily high degree. How does this relate to what I said on the previous slide? Well, it turns out it's the same thing. If you want this for degree k-1 polynomials, then you'll just use the monomial basis. And you'll say that for all j less than equal to k, I want expectation cx times fx raised to j is expectation cx times fx raised to j minus 1 times f star of x. Right? So indeed, these two things are exactly the same. Was there a question?
Maybe I'll ask a question, Parikshit. So in the sufficiency, I mean, if I think about a polynomial that has lots of monomials, I sort of pay something in the air.
Yes, so you have to bound, you're allowed to take polynomials of any degree. And if for each of the basis monomials, you get error alpha, if you take a polynomial of L1 norm, let's say D, you'll get D times alpha in your multi-accuracy error. Right? So yeah, the L1 norm will factor into it. Does that answer your question?
Yes.
Okay. All right. So this allows us to define this, this collection of fairness notions, which I call the multi-calibration universe, or MCU for short. This is a hierarchy that interpolates from multi-accuracy to multi-calibration at the highest level. And, as you go higher up, the strength of these notions increases, but also the computational complexity. So what is the hope here? The hope is that a lot of the desirable properties of multi-calibration, they actually hold at low levels of this hierarchy. And secondly, that you actually get it's that the lower levels, the sample and computational efficiency are more like multi-accuracy, which is really cheap, right? And, there is a strong analogy here that we'd like to draw to pseudo-randomness and things like the sum of squares hierarchy. In pseudo-randomness, for instance, we know that one-wise independence gives you nothing, but pairwise independence is magical, right? And we're hoping that something similar will happen even with these fairness notions. So does it? Let's talk about that. So there are two things I need to convince you. One is that computation is much cheaper at low levels of this hierarchy. And second, that you're getting interesting fairness guarantees here, fairly low in the hierarchy. Okay, so let's do the efficiency part first. Let's generalize and define this notion called weighted multi-calibration, at which point I try and answer Avi's question from a long time back. So what is weighted multi-calibration? I'm going to allow a family of weight functions, W, which map 0, 1 to 0, 1. W is intended to be applied to the predictor, right? So weighted multi-calibration, we say F is C, W multi-calibrated if for every C in C and for every weight function W, expectation Cx, W of Fx times Y minus Fx is 0. So this is a unifying framework for thinking about all these definitions we've seen so far. What we call full multi-calibration, the original definition of multi-calibration, the weights are the indicators of these kind of interval functions, right? Rather than asking, is the prediction exactly equal to V? Let's just ask, does it lie in some narrow interval of width alpha, right? So by taking this collection of weight functions, you get the original definition of multi-calibration. Smooth multi-calibration is where the weights are all one Lipschitz weights. Rather than doing these delta functions, which are discontinuous, you only allow Lipschitz weight functions. And the reason to introduce this notion is because it's a more robust notion of multicalibration. It allows you to do small perturbations of the predictor without the multicalibration property going haywire, right? This is a multicalibration analog of notions that have been studied in the forecasting and game theory literature previously. Low degree multicalibration is where your weight functions are all polynomials of degree k, right? Or rather those polynomials of degree k which are bounded in the range 0, 1. Multi-accuracy is the setting where the weight function is the constant 1 function. So I like to think of smooth multicalibration as, let's, instead of thinking of the original definition of multicalibration, let's think about smooth multicalibration. It has a number of nice properties. So you can think of our quest as trying to interpolate between the constant 1 function and the set of all 1 Lipschitz functions. One way to do this interpolation is to use low degree polynomials. Okay. So the efficiency, basically the HKRR algorithm works in this setting, right? What you do is, once you fix a particular weight function W, you are faced with a weak agnostic learning problem again, because the rest of the stuff, WFX times Y minus FX, is just some real value in the range -1, 1. Finding C correlated with it is a weak agnostic learning problem. You have a violation, you fix it, you make progress by alpha squared if the violation was alpha, so you can keep going, right? So there's nothing much going on here. The running time is linear in the number of weight functions in your family, because you might need to explicitly run down the list and check for a violation. The sample complexity is rather subtle, right? It's subtle because the sample complexity to achieve error alpha for each basis element is 1 over alpha. But as Guy hinted at before, when you have a large basis, you're going to lose something when you take linear combinations of these basis elements. So you shouldn't be surprised if the error for each basis element needs to go like alpha over the size of your basis, right? So a large basis could actually cost you considerably in terms of sample complexity. But let's just ignore this issue for the time being. Okay. Now let's ask the question, is low degree calibration actually buying us something in terms of efficiency? We'll do this comparison in high dimensions, where the number of labels is D. So when you do degree K multicalibration, the weight function is all monomials of degree K in D variables, which is something like D to the K. I want you to think of K as 2. So this is just D squared, right? Whereas when you try to do smooth multicalibration or full multicalibration, then you have to take all subcubes of a certain weight delta in D dimensions, which is exponential in D, right? So clearly everything, the running time, the sample complexity, and so on, are exponential in D for doing full multicalibration, but they're just polynomial in D for smooth multicalibration, right?
Parikshit, what is D? Is D the output label?
Number of labels, yeah. So imagine you're doing multi-class classification where you're trying to, assign 1 of 100 labels, right? And then you're trying to check multi-calibration and so on. Even checking multi-calibration involves conditioning on a D-dimensional vector, and there are exponentially many D vectors to check. That is the issue that we're trying to get at here. If you're trying to do low degree multi-calibration, everything now scales polynomial in the dimensionality.
So do you, sorry, it wasn't clear to me in the beginning that you were moving to a multi-label setting.
Oh yeah, that I just did it for this one slide to consider the efficiency, because the inefficiency of multi-calibration is most pronounced when you consider the multi-label settings. There are also efficiency gains to be had in the binary classification setting, but I won't talk about that now. Right?
Okay, great.
Yeah. In terms of sample complexity, again, there is a pretty large gap. To do degree K multi-calibration, you just have sample complexity, which is something like D to the K, versus exponential in D if you're trying to do full multi-calibration. And in fact, both of these are upper bounds. The upper bounds for low degree multi-calibration was improved to K log B by Pranay Tankala, who is a grad student at Harvard. He just communicated this to me recently. I think the exponential in D is inevitable. I'm guessing there is a lower bound which says that you need exponential in D many samples to achieve full multi-calibration in D dimensions. Right? Anyway, going back here, I hope I've convinced you that the efficiency improves greatly when you're considering low degree multi-calibration. Now the question we need to answer is, well, what is it good for though, right? Okay, so the main thing that it's good for is disallowing overconfidence in your predictor. Now, this is not a precise statement, but I'll give you a couple of formalizations of this notion. So let's consider this setting here, where there is not multi-calibration. This is just calibration really. C is the entire universe. The ground truth F star is that every point has the same probability 0.5 of being 0 or 1. This predictor G though, it arbitrarily takes half the population and predicts 1 for that half. It takes the rest of the population and predicts 0, right? Now, this predictor G is multi-accurate because in expectation, or accurate really, because in expectation it's correct, but it's not multi-calibrated because when it says 1, the expected label is 0.5. When it says 0, the expected label is still 0.5, right? Now, this is exactly the kind of thing that multi-calibration disallows. It disallows making arbitrary distinctions between populations that have no basis in the data, right? So this is multi-accurate, it's not multi-calibrated. Is it in MC2? Yeah.
Just wanted to point out that it's almost 12:30. So I don't know how
Okay, I'll just, I'll do a couple of, maybe I'll just finish this example and then cut to the chase. Yeah. Okay, so is this thing in MC2? So what is MC2? MC2 is these two constraints, right? The expectation of y minus fx is 0, and the expectation of fx times y minus fx is 0, right? It turns out that actually this predictor, it doesn't satisfy this second constraint. Now we could, and there's a pretty simple explanation for why it doesn't. It turns out that if you are in the second level of the hierarchy, your predictor needs to satisfy the following condition, that expectation of fx squared conditioned on C is no more than the second moment of the base optimal predictor conditioned on C. In fact, it's at least also the expectation of that thing squared, but that's not the important thing. The second moment of your predictor conditioned on C cannot be larger than the second moment of the base optimal predictor. Another way to say the same thing is that the variance of F has to be less than the variance of the base optimal predictor, right? And this tells us that G is not in MC2 just because it has non-trivial variance. And things in MC2, they cannot, in this particular example, where F star has no variance, your predictor cannot have any variance either. So let me just say that this is a special case of something which happens in the kth level of this hierarchy, where in place of moment matching, you get this following nice inequality, which I call moment sandwiching. Your expectation of f raised to k is equal to the expectation of f raised to k minus 1 f star, right? This is just the definition. But then as you keep decreasing the power of f and increasing the power of f squared, you get this nice chain of inequalities, culminating in this interesting moment inequality that the kth moment of your predictor conditioned on C is no more than the kth moment of f star conditioned on C. And by itself, if someone came to you with a predictor and claimed that it satisfies this inequality, I don't know how you could verify this. Right? Again, in analogy to derandomization, I think this is a very natural guarantee to have. Remember, our first attempt at moment matching was to say that these two things should be equal. We didn't quite get that, but we got an inequality going in one direction. In analogy to derandomization, we didn't know this previously, even with full multi-calibration, but only having degree K multi-calibration, it makes this very natural, right? Okay, so I'm out of time here, so I'm going to skip over a bunch of other things and just say this, that what is the goal? Let me just try and convince you that low degree calibration actually gives you some of the good properties of full multi-calibration. So modern DNNs, they are just not calibrated. This is well documented. They tend to be overconfident in their predictions. If you look at this graph here, what it says is that ResNet, which is currently one of the best image recognition networks there is out there, when it predicts labels with a probability of anything between 0.25 and 0.75, it essentially means nothing. It can say that I'm 75% sure, but the probability that it's actually correct is something more like 25%, right? These things are just very poorly calibrated. Now, they're overconfident in their predictions. It's not just a calibration problem. They are constantly overconfident in their predictions. Calibration is one way of auditing confidence. It audits it value by value. It insists that when the predictor says something happens with probability 0.7, then actually that thing happens with probability 0.7. When it says 0.5, stuff actually happens with probability 0.5. Low degree calibration is in some sense auditing this confidence, but it's auditing it using moments. This is something that we do all the time in pseudo-randomness. We are saying if the distribution of fx and y conditioned on fx, if these things are very different, then in that case, there's probably some small moment I can compute, which will show me the difference between these things, right? So in some sense, whereas full-blown calibration does this auditing for confidence by looking at conditioning on each and every value of the predictor, what low-degree calibration does is something similar, except that it uses moments to do the same auditing. In this sense, I think it's a very reasonable way to get the power of calibration and the utility of calibration, but at much lower cost. So the time right now is 9:30. In fact, I'm 2 minutes over. So I'm going to stop right there. Now, there was some other stuff which I planned to talk about, which, I'm happy to, if anybody is not hungry and has time to kill, then I'm happy to talk to you afterwards. But let me just close by saying that we've talked about these three notions: multigroup fairness, loss minimization, and indistinguishability. And we've seen there's very close connections between these three. We saw it through this notion of omniprediction. We saw that using this lens of indistinguishability and thinking about it as some kind of a derandomization gives efficient notions of group fairness. I didn't get a chance to talk about how you do omniprediction more efficiently, short of full-blown multicalibration. But again, there is a derandomization way of thinking about that. This leads to some intermediate notions of fairness, which I think are interesting in their own right, such as low-degree multicalibration, which I did talk about, multi-accuracy plus calibration. This is something I didn't talk about. Think of it as multi-calibration light. It gives you some of the nice properties of multi-calibration as far as loss minimization goes. And the goal of this line of work, what I've discussed so far, is theoretical work, but it has been applied in practical settings. Guy has been involved in some of this work, and he can tell us more about how it's been applied in medical scenarios, for instance. The overarching goal of this work is to achieve rigorous but practical notions of multigroup fairness, which can be actually used and applied in real machine learning models. And starting next week, I'll be joining Guy at Apple AI Research, where I hope to take this agenda further. So thank you all very much.
Thank you. Any quick questions? Not quick.
I don't want to torture everyone, but I can definitely ask a question.
Go for it. Yeah.
So Parikshit, one of the things, the distinction between calibration and accuracy is that when you're trying to train, calibration is sort of circular. You train your predictor, you sort of see that it's doing something bad somewhere, you fix it, and now you want to go again, but there's a circularity kind of. You're comparing a predictor that was trained on data to the data, and you might be overfitting, so you need to do something, draw fresh samples. There's a kind of circularity that takes place during training, and at least empirically, I think it's been observed that it can cause overfitting or require more samples, even in the Boolean case. So I'm wondering, do you have any thoughts? I mean, do any of these notions avoid or kind of bound the amount of circularity you can get? Does the question make sense?
Well, kind of. I think the moment you have a weight function, which depends on the predictor itself, there is some level of maybe you call it circularity, which I'm not sure is necessarily a bad thing, right? Like if a predictor is making some predictions very often and some other predictions very seldom, you really need to concentrate on the predictions that it makes more often and check the validity of those predictions, right? So, well, certainly these notions, they address the sample complexity issue, right? It's a smooth interpolation between multi-accuracy and multi-calibration. So if you do degree 2 multi-calibration, for instance, it doesn't require a lot of samples at all. Rather than conditioning on particular values of v, you're just, taking y minus fx, multiplying it by fx and seeing if that thing satisfies multi-accuracy. So again, certainly I think
I see that distinction in the multi-label case, but I don't see it in the Boolean case.
well, even in the even in the Boolean case, this thing is the way I'm describing it. It all applies. Look, in multi-accuracy, you just check cx times y minus fx is 0. Now I'm telling you to check one more constraint: cx times fx times y minus fx is 0. Right? That's kind of checking second moments. And well, maybe we can talk about it. I guess to really answer your question, I need to know what exact. I don't think these things will overfit, because they are not very, it's really very sample-like. This is a small addition you make on top of multi-accuracy, which gives you some extra power. And then you can go on to checking third moments, fourth moments, and so on and so forth. But, I am pretty certain, and experimentally also, we've seen that in terms of sample complexity, this is much lighter burden than multi-calibration.
Great, thank you.
Okay, thanks again for a great talk.
Thanks, Ben.